Okay, thank you. Thanks for including me, even in this remote way. I'm going to tell you about some recent work with my collaborators, Shean Lim, who is assistant professor at Xiamen University, Malaysia, and also Yulong Lu, who's assistant professor at University of Massachusetts, Amherst in the US. Much of the work I describe has appeared already in Sci Math Analysis, so you can find more details there. I'll also describe some ongoing work that we haven't submitted yet. In any case, feel free to contact me and we could set up some discussion afterward if any of you are interested. So our work and this talk is about spatially distributed chemical reaction networks. And we're interested in better understanding the bridge or link between stochastic microscopic models and macroscopic PDE description, both of which are used commonly in the biochemistry community. So the kind of stochastic models I have in mind involve a finite but large number of particles of different types, different chemical species, and they diffuse in space, in a continuum, in Euclidean space, or on a torus, or on Riemannian manifold. And then the chemicals react with each other in various ways, in a way that depends on their spatial proximity. So I'll use this, the common chemical reaction notation, to indicate, so in this case, a molecule of species A can react with two molecules of species B to produce a molecule of type C and one of type D. And so when this occurs, the molecules of A and B vanish and leaving C and D. So this notation doesn't say anything about the spatial movement and how that's related to the reactions. This just says that one of the possible reactions that can occur would be this one. Okay, so these molecules are diffusing and also reacting. So the PDE description that we have in mind is a system of equations, reaction-diffusion equations of mass action type. It's a system, so each component in the system corresponds to a concentration or density of one of the chemical species involved. And the reaction term, this is a nonlinear vector field that encodes the mass action kinetics. So for example, just considering this type of reaction, the PDE would have a nonlinearity involving terms of this form. For example, the component associated with species A would have a loss term, which is proportional to the concentration of A, and then the square of the concentration of B, because two molecules of B are involved in the reaction with A. And there would be a corresponding gain term in the component associated with chemical D, which is produced by this reaction. So the basic question is, how do we pass from stochastic model to the PDE? And can we do so in a quantitative way to understand how these two models may differ? So before I explain the setup more precisely, let me give some context and say something about related works. There is a lot of work on chemical reaction networks. These are ODE models with no spatial structure. The mathematical theory was set forth in these seminal works of Horn and Jackson, also Feinberg. These involve nonlinear systems of ODEs with algebraic nonlinearity. There are also several works on stochastic models and how the stochastic models may approximate chemical reaction networks. For example, Tom Kurtz in the 70s showed that certain stochastic models driven by Poisson processes converge to these chemical reaction network systems of ODEs, and also he derived some central limit theorems. There's a nice recent book surveying a lot of work that's been done in this area by Dave Anderson and Tom Kurtz. And then more recently, there's also been work on large deviations for these Poisson-driven models, but again, without any spatial structure. As has been discussed already, there are various interacting particle systems with spatial structure that give rise to reaction-diffusion equations of various types. For example, the work of Damasi, Ferrari, and Leibowitz has been mentioned. They study spin systems, an exclusion process on a lattice, and its convergence to a scalar reaction-diffusion equation. Related work of Duret and Neuhauser studied spin type systems and lattice, giving rise to systems of equations. Our work and the model we look at is closer to the work of Ohlschlager, who studied particles diffusing in a continuum and interacting through a kernel. In the convergence, he studied convergence to reaction diffusion equation. The kind of reactions that he covered in his work was somewhat limited to branching processes such as A going to 2A, or a single type change, one species converting to another type, or possibly annihilation, a species, multiple species combining and then annihilating. So we're interested in exploring a more general framework for more general mass action type kinetics, and also obtaining some results that are more quantitative. And I'll point out some recent work of Flandoli and collaborators. I'll come back to this later. This is on in a continuum in one dimension with the KPP Fisher type equation. So let me describe the stochastic model more precisely. So the stochastic model involves an ensemble of n particles. Think of n as being large. And each particle has both a position and a type. So we use x for the position, and this will be in Euclidean space, or actually the let's say the torus in RD. And the type is the chemical species ranging from 1 to some fixed number of types in T. So the state variable for a single particle, I'll denote by y, it's both a position and a type. So we assume that particles move around in space, they diffuse independently, and we could assume that the rate of diffusion is type dependent. So each particle is driven by an independent Brownian motion. You could also add some drift here that's dependent on type, or even our current work includes the possibility of some McKean-Vlasov type interaction where the drift depends on the empirical measure of all the particles. But for simplicity, let's suppose that each particle is driven by independent Brownian motion. So naturally, in the limit, we'll obtain, in the limit as the number of particles goes to infinity, we'll obtain a PDE which has a diffusive term. So the component associated with type C will have a diffusion term, perhaps the diffusivity depending on the type. The reactions produce a change in type. As I said, they're in particles. There may be multiple kinds of reactions that can occur in the system. For simplicity here, I'll suppose that all reactions are bimolecular. And by this, I mean that each allowed reaction has both 2 inputs and 2 outputs. Possibly the species involved could be the same, but each one has 2 inputs and 2 outputs. And thus, the total number of particles is conserved through these reactions. So a reaction is specified by the input types and the output types. So here, this notation means that this reaction involves input type K reacting with input type L to produce reactants of type K prime and L prime. Okay. So again, a finite number of chemical species and a finite number of reactions are allowed, but these could be arbitrarily large. Okay. So because reactions are assumed to be bimolecular, the number of particles is conserved. So for example, maybe we're looking at species A, B, C, D, E, and 2 of the reactions that might be possible would be A and C combined to produce B and C. So here, chemical C is acting as a catalyst, catalyzing the conversion of A to B. Or all different species could be involved, B and D, going to A and E. So these reactions may occur simultaneously. Our current work involves extending these results to the case of a general finite order reactions. We would have, say, M inputs and M outputs. This says nothing about the spatial structure. So the particles react in a way that depends on their spatial proximity. And this is described through a kernel. For each reaction, there is a kernel, phi r, which depends on, which is a function of the spatial location of the input chemical species. So this diagram is illustrating, let's say, a type K particle, the red particle here, reacting with the type blue particle. So they're moving around in space, and as they get closer, they become more likely to interact. So this kernel is a function of the position of the type K particle and the type L particle. Right? And we could say that when they react, the new particles appear at a different location. That would involve another kernel. But for simplicity, we'll just say that when they react, the two input particles just change type to the output particles. So you can think of this reaction kernel as something that's localized, approximating the identity, the delta. Of course, if phi were a delta function, then there would be no reaction at all in dimension 2 or more, because with probability 1, two particles would never occupy the same site. We will assume that the kernel phi is an L infinity. This will play a role in the result, as I'll explain. Another way of describing this kind of interaction is through a family of independent exponential random variables, clocks, you might say. So you could say that for each pair of particles in each type of reaction that can occur for those pairs, there is a clock that rings at a random time, and conditioned on all the particle paths, these clocks are independent, the times are independent. So for these two particles, y1 and y2, which are inputs to this type of reaction, given the path of those particles, the distribution of the time at which the reaction occurs is exponential with this rate that is a function of the path. All right, so here's a summary cartoon, the picture I have in my mind of the system. There are n particles moving in the state space, and the state space is a product of Euclidean space, the product of Euclidean space with 1 to n being the number of types, right? So I think of this as different layers. Each layer corresponds to particles of a certain type. And so these particles can move, they move horizontally in the layers. That's the diffusion on the spatial domain. And then let's say when a gold particle here, type 5, gets close enough to a type 4, then they may react and produce new types, which would be hopping down to some other layers, say 3 and 2. And simultaneously, you can have reactions between other types, say type 1 and type 2 can combine to form type 4 and type 3. So when they're close, they may undergo this jump. Whereas here, there's this gold particle could react with green, but it's unlikely to react with any of these greens because it happens to be far away at this time. So what happens as n goes to infinity, as we increase the number of particles, we expect that this system could be described by a system of PDEs where we have a density on each of these layers corresponding to the concentration of each chemical species. So I was just describing the mean field PDE. It's a reaction diffusion equation of mass action type. So it's a system, okay, for the component associated with chemical Xi would have a loss term and a gain term. So the loss term is proportional to the density of Xi. And then here we're summing over all possible reactions that involve Xi as an input. and C reacts with some other species type L to produce some other chemicals, okay? And then there's a gain term, which involves all possible reactions that have C as an output, right? Now, this is actually a non-local equation involving the kernel phi. That's the kernel that controls the rate based on proximity of the particles. Formally speaking, if we chose phi to be a delta function, then this would be usual quadratic mass action type nonlinearity, which is local. But from the point of view of the stochastic model, choosing phi to be a delta function would preclude there being any reaction except in. Okay, so to compare these two systems, we consider we're going to apply the method of relative entropy. So we think about the state vector for the entire n particle system. So this is a product space, n copies of Euclidean space and.
Sorry.
Yes.
James, there is a question in the chat.
Oh, yes. I'm sorry.
From Michele Aleandri. So what are the general hypotheses on phi r?
The question, I was saying phi r is an L infinity, but we're not assuming regularity other than it's bounded and has a density.
Okay, thanks.
Okay. So we look at the law of the coupled n particle system. Okay, so that's rho n. So this is a probability measure on this n-fold product space. And we compare that with rho bar n. This is a product measure on the same space. It's n copies of the solution to the mean field PDE, right? So think of rho n as the law of the true particle system, the coupled system. And rho bar n is related to the mean field PDE. Okay, so as I mentioned, our analysis is based on the relative entropy method, as was discussed in the mini course of Professor Jara last week. This originated with the work of Yao. Our approach was inspired by recent work of Jabin and Wang, who looked at particles interacting through singular drift. So the object of study is the relative entropy between rho n and rho bar n. Again, this is the rho n is the law of the density for the true system, that is the coupled particles, and rho bar is related to the solution of the mean field PDE. Both of these depend on time. So in Professor Jara's lecture, someone asked a question about when it might be interesting to consider a reference measure that depends on time, but this is one case. So that the system is not in equilibrium. Rho bar n is changing, but it's the natural object to which we compare over a given time horizon. So the result is an estimate on this relative entropy. There are two terms. There's one term involving the initial relative entropy. And so this would be 0 if we assumed, say, that the particles were sampled initially independently according to the mean field solution, rho bar. And then there's another term related to possible growth of relative entropy and the growth of correlations due to the reaction. And so this is an estimate over a fixed time horizon, and says that as n goes to infinity, the relative entropy converges to 0 if it converges to 0 initially. Notice that the kernel plays a role in the estimate here through phi infinity. So in principle, we could also shrink the kernel. The kernel could contract within in a way that is logarithmic. We would like to obtain a result that allows us to shrink the kernel at an algebraic rate, but that's not permitted by the current estimate. One consequence of this is a propagation of chaos that says that as the number of particles goes to infinity, if you look at any fixed number of particles, say the first m, then the marginal density for those m particles converges to a product law, converges in L1 to the density, which is the M-fold product of the mean field measure. This is a consequence of the Pinsky's inequality. And the error, because you have the 1 over n error here, then the error would be 1 over root n, assuming that the initial relative entropy is of that size. Okay, let me just say a bit about how this analysis proceeds. So the law of the coupled system satisfies the Fokker-Planck equation. Here you have the diffusion. I've just set all the diffusion constants equal to 1. And then this is the generator, part of the generator associated with the reaction terms. Then rho bar n, which is the product of the solutions to the mean field equation, it doesn't satisfy the same equation. It satisfies a nonlinear system, but we could write it as, you could think of this nonlinear equation as a perturbation of the linear equation, the Fokker-Planck equation. And so this term k, this is a nonlinear functional, which captures the difference between the generator for the true system, that is the coupled system, and the nonlinear term for the mean field equation. So when you compute the relative entropy, part of the work is to show that in fact you can take a derivative, and all these calculations are rigorous. So one can compute a derivative and show that there's a part that's dissipative, that's always non-positive, and then there's a part that potentially could grow, and this growth is related to, of course, this nonlinear term k, right? So effectively, this is a growth rate of the solution to the mean field equation, or the expected value of that, sampling according to the measure rho n. Okay. So to estimate relative entropy, one needs to control the growth of this term. And so for this, we use the change of measure, or entropy inequality, as Professor Jar mentioned. This is a consequence of the convexity of the entropy functional. So this is the term that you need to estimate is an expectation with respect to rho n, and this entropy inequality allows us to put this in terms of rho bar n, which is a product measure. And so perhaps it's easier to estimate integrals with respect to product measure. And so then all the analysis is related to estimating this term here. And for that, I'll kind of just briefly say, since I'm running out of time. So for that, we have a large deviation type estimate, which applies to random variables of this form. So the term here involves the binary, the bimolecular interaction, and so we have a large deviation estimate that's key to estimating this, and it's something like a Zuma's inequality for sums of martingale differences. So we're working with something that's in L infinity because of the assumption on the kernel. So let me sum up by saying our ongoing work. In our ongoing work, we've extended this to balanced reactions up to any fixed order. So you could have, single particle going to single particle, and then higher order reactions, including m particles converting to n particles. And this involves the m-body version of this large deviation estimate that I mentioned. With Andrea Agassi, we're also looking at non-conserved particle numbers. So this requires a different framework because of the non-conservation. So there you have to look at Fock space and probability measures in Fock space. Also, with general chemical reaction networks, you have the possibility of blow up. So the geometry of the system plays a greater role. There's also some recent work of Isaacson, Ma, and Spiliopoulos on non-conserved systems within the framework that Buschlager developed, which I mentioned already. Another interesting issue that we'd like to better understand is the interaction range. So I said phi is an L infinity. You would expect that if you shrink phi in a certain way, that maybe you could recover the local reaction diffusion limits. But there's a critical scale. If you shrink phi too fast, if the kernel concentrates too fast, then you don't see any of the reactions in the limit. So it's conjectured that if, as long as this exponent beta is less than 1, then you would see the correct reaction diffusion limit. There's some work along these lines by Flandoli and collaborators in this one-dimensional system I mentioned. They proved that one gets the correct limit for beta less than half. So sort of understanding that in this more general setting is an open problem. All right, I'll stop there. Again, feel free to email me if you have further questions you would like to discuss. Here are several references that I mentioned. Thank you.
Thank you. We are perfectly on time. We have time for a fast question.
Hi, thanks for the nice talk. I was wondering for the non-conserved interaction, would you still use again entropy methods? And if yes, what is the counterpart in this setting for the large deviation estimate?
Well, great question. Well, the first part, yes, that's what we're working with. So you have to look at the entropy conditioned on there being a certain number of particles at a certain time. For the large deviation estimate, I don't know. We haven't figured that out. So for the multi-dimensional large deviation estimate, I'll just leave this here. So you're looking at functions of many inputs which satisfy a marginal mean zero condition, and you prove that sum of these functionals has an exponential tail. So I don't have a good answer to your question with non-conserved systems.
Okay, so thank you again for the nice talk.